Hello, pre-calculus people. Hope you're having a fantastic day today. This lesson tends to go a little long, so I'm going to try and get through it just as quickly as I can here, but try not to rush it, just for the sake of everyone's sanity. Okay, so we're talking about polynomial applications, and the topic here is an open box, and that's basically like a box, a rectangular box with no top on it. Right, it's what they call an open box. So this one says that an open box can be made by cutting out squares from the corners of a 9-inch by 12-inch rectangular sheet of cardboard and folding up the sides. Find the dimensions of the box that maximizes its volume. So here's the key word here is maximizes. All right. And the volume. So let's draw a little diagram real quick of what we're talking about. I've got a sheet of cardboard that is 9 by 12, and it says that an open box can be made by cutting out squares from the corner. Here's what they're talking about. If I cut out this square and then cut out a square down here, I can fold it along this line, and this is now the wall of the box when it folds up. So that's kind of what they're doing here. Let's go through and finish this out. Now the thing about squares is these would all have to be the same size, right? You can kind of imagine this. Alright, so the squares would all have to be the same size, but we don't know what size they are. And we're trying to find the volume. Well, if you'll remember, volume for a rectangular prism, which is what this will be, a box, is the area of the base, which is length times width, times your height. The question is, what's the height? Well, if this side right here is going to be folded up, right? It's going to be folded like this on top to where it's standing vertically, then that means that this distance right here is going to be my height of the box, right? So I'm just going to call that x. And that makes all the little corners x because these are all the same, right? Alright, so the length, now the length is not 12. It's not 12 because I'm taking out these little x's right here. I'm taking out 2 of the x's. So your volume function here, volume, which is a function of x, is going to be the length, which is 12 minus 2x. See, we're taking out 2 of those x's from our length. And the width, which is 9 minus 2x. Again, we're taking out the x's from 9, taking away 2 of those x's from the distance of 9. Alright, so volume then is going to be your length, which is 12 minus 2x, times your width, which is 9 minus 2x, times your height, which remember, if we fold the edge of this box up, this x right here, that's going to be the height of our box. So you can see how if we made these squares much bigger, that we would have a taller box, but it would be a lot more narrow. The base would be a lot smaller, right? But on the same side, if we make these squares really small, we're going to have a really wide, flat box, but it's not going to be very tall. Okay, so I've got this thing graphed in a calculator here. I just went to y equals and typed in that same graph, and here it is. There we go. So I'm going to go through and find my important information like my zeros. My window is set from 0 to 5 on the x-axis here. So just kind of follow along with me while you're doing this. My 0 is 4.5, so I'm going to come over here and I'm going to put a point right here and I'm going to call that 4.5. Next I'll need my maximum, and here's my maximum. So I'm going to put a point, let's call it here. I'm going to call that 1.697 comma, I'm sorry, that's kind of bright, 1.697, let me bring that down just a hair, there we go, and it's 81.872. And if you notice the shape on this, it kind of goes, starting from 0, 0, kind of goes up like this, like it's going to make a parabola, and then it hits a maximum, comes back down, and kind of starts to level out again. Just so you can see this here, let me go back to my window. I just want to show you what this thing actually looks like, because it's a cubic function, right? So that's what it actually looks like. It's a cubic function because you're multiplying 2x, 2x, and x, so it's going to be cubed. So you're going to come back up here, but remember what we're doing is we're coming up with x being the height of the box. Well, we can't have anything more than 4.5 because then it goes negative. So what I did is I just went to my window and chopped that piece off. I also know I can't have any negative pieces, so I'll chop that off as well. And I'm going to restrict it down to this. If you don't restrict it, it's going to look like this thing keeps going forever. And that's a no-no. Alright, so that makes my domain 0 to 4.5. My range will be 0 to 81.872. And it says, what is the maximum volume that can be enclosed? Well, that goes back to my graph. X down here represents my height, right? What does my Y values represent? Well, they represent my volume. So what is the maximum volume that you can attain? Well, it's going to be 81.872 inches cubed. A lot of people get confused on this. Why is it cubed? Why cubed? Why not inches squared? Why is area squared and volume cubed? That has to deal with how many dimensions is it. You're multiplying this many inches by the width that many inches by the height that many inches. Inches times inches times inches is inches cubed. It means it's a three-dimensional object. And then down here for your length, all right, I've got length is 12 minus 2x, so I'm going to do 12 minus 2 times my x value that gave me my maximum volume is 1.697. Alright, so I'm just going to write this down here so I can show you what I'm doing. I'm doing 12 minus 2 times 1.697. And I'm using that because that's my x value that gives me my maximum height. And that is 8.606. Do the same thing for your width. 9 minus 2 times 1.697. That gives you 5.606. And I'm sorry, these are inches. Inches, and your height is just the x value, 1.697 inches. All right, so just a little bit of common sense, a little bit of practicality for your mathematical minds to ponder. The box with the lid. So now we have a box with a lid. Two congruent squares are removed from one end of a rectangular 10-inch by 20-inch piece of cardboard. It says two congruent squares are removed from one end. That's talking about these guys right here. One square, two squares. Of a 10 by 20. So the dotted line on the outside represents your 10 by 20 piece of cardboard. So I'm going to go ahead and do this. This is 10 from here to here. This is 10. And this is 20 from here to here. Two congruent rectangles are removed from the other end as shown. Determine the value of x so that the resulting box has a maximum value. Okay. Well, just a little bit more information on this here. Oh, I'm sorry, I messed up that line on that 20. That 20 goes all the way out here. Just saw that. Ding. Bing, 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 bing. Okay. Now, the key to doing this is understanding that one of these is going to be a square. See this inner dashed line right here? is a square, right? From here to here to here to here. Well, how big is that going to be, really? So let's look at this side right here. We had 10, and we're going to take away this x and this x, the ones that we cut away. So this dashed line is 10 minus 2x. This line over here, if you look at what is happening, we've got a rectangle, a square, a rectangle, and a square. What that tells me is that if I want this thing to be a box, these two rectangles have to be congruent. And these two have to be congruent. Well, what that tells me is that this divides this 20 in half. Again, if you want it to be a box and if you want it to fit nicely, this square or rectangle or whatever it is and this rectangle have to be the same as this rectangle and this rectangle, right? Now, I don't have to have a square here. It can be a rectangle width-wise anyway. So what's that going to do to me? Well, that makes this 10. If you cut your box directly in half, that's going to make each half of it 10, right? So that means this line is 10 minus one of the x's. I'm cutting one of the x's out of this chunk of 10 from here to here. I'm taking this length of x, taking it out of 10. So that's 10 minus x. Okay? So let's do some math, some mathy stuff to it. Let's come up with volume, right? We're trying to write a function for the volume of the box. All right, so volume v of x is going to be equal to, and I need the length, width, and height of the box. Well, the length is 10 minus x. Remember, this is after it's all folded up, right? The length is 10 minus x. The width is 10 minus 2x. And the height itself, the height of the box, again, will just be this piece of x. So I'm going to go back to my calculator now, and I'm going to type in 10 minus x, 10 minus 2x, and x. And let's see if we can come up with something that's going to look a little bit correct, at least. Let me zoom out just a hair. Alright, I found a good window here. This is 0 to 7 and 0 to 150 on the y-axis there. So it looks good, right? I'm going to need my y-intercept here, so I'm going to go down to 0, or excuse me, x-intercept, so I'm going to go to 0 and enter, and enter, and enter, 5. Okay. So it's going to come over here and it's going to touch at 5. Find my maximum real quick. 1, 4, and I've got a maximum at, sorry, let's go right here, 2.113, comma, 96.225. All right, it's going to be roughly it. So my domain will go from 0 to 5. My range will go from 0 to 96.225. It says, what is the maximum volume that can be enclosed? Well, that's going to be the 96.225 inches cubed. Your length is going to be 10 minus the x value here, 2.113. So length is going to be 7.887. Width is going to be 10 minus 2 times 2.113. 7.774. Ooh, wow, I did that wrong. Hang on. I typed in a 12 instead of a 10. Ah! Let's try that one more time and actually type in the correct numbers this time. There we go. 5.774, and your height is just 2.113. Alright, so it's not too bad once you get used to it, once you understand where we're all going with this, and these are all inches, right? All right, last one says the package. A package may be sent by mail only if the sum of its height and the perimeter of its base are not more than 72 inches. Right? The sum of its perimeter, or the sum of its height and the perimeter of the base is not more than 72 inches. Find the dimensions of the box that would maximize volume. That can be sent if the base of the box is a rectangle with a length equal to 2 times its width. Blah, blah, blah. Okay. I'm going to start off by drawing a box. It is a box, right? So I'm going to draw a box, a little three-dimensional box here. I don't know if it's a square box. It says it's rectangular, so I'm just going to assume that it is not a perfect square. Right? And it says that the perimeter of the base is not more than 72 inches, or excuse me, the sum of the height and perimeter is not more than 72 inches. So you've got 72 inches that you can work with, and that's your perimeter of the base plus your height. Right? That's the perimeter of the base plus the height. And then it says find the dimensions of the box that will maximize volume if blah 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 if it has a length equal to 2 times its width. So if you have a width, we would call it x, and if you have a length, we would call it 2x, right? So the perimeter then, the perimeter along the base of the box, if you can imagine this here, is going to be 2x plus 2x plus x plus x. So 1, 2, 3, 4, 5, 6x, right? So 72 is equal to 6x plus your height. So I just came up with the perimeter. It's 6x. Fantastic. Now you can come up with the height. So the height is 72 minus 6x. Solve for h. 72 minus 6x. That's the jump there. Understanding that the length is equal to 2 times its width. That's the key to unlocking the whole sum of its height and perimeter of its base. The key to unlocking this is that the length is twice its width. So I can pick a letter like length or width, and I can express it using x. And once you do that, then you can express the other one using x. Now we're doing volume again, so v of x is 2x times x times 72 minus 6x. Length times width times height. Going to my calculator here. 2x times x times 72 minus 6x. All right, so this is going to be a pretty big function if I had to guess, unless I miss my mark. I'm going to change my window to being pretty large. Let's change this. Alright, looks like I got something workable here. Alright. Good grief. There we go. So this is going to go through 0, 0. Got something I can work with now here. Again, I don't really care about the left-hand side. Mainly what I care about is the positive portion of it. I have a 0 at 12. And a maximum at 7.9999999 blah blah blah. I'm going to call that 8. So at 8 comma 3072. And that's basically what you're looking at. Domain is 0 to 12. Brackets, range is 0 to 3072. Maximum volume 3072, and we're talking about inches cubed still. So your length is going to be twice of the x value, so your length will be 16. Width is just x, which is 8, and h is 72 minus 6x. So 72 minus 6 times 8, 24. So not too crazy of a lesson. A lot of box building, a lot of optimization. We call this optimization. It's maximizing junk. And that's all I have. So have at it.